So we already did this slide, but honestly, instead of saying the best bet is this idea of weakly interacting massive particles, something that's like something different than a proton or a neutron or electron, some other particle. Actually, physicists will tell you there are definitely different smaller particles than the three we talk about in chemistry. But in addition to WIMPs, we really think that there are objects out there that are actually what we call machos instead of WIMPs, massive. Massive, they're usually in the halo region. That's the H part of machos. So on to WIMPs. And actually, when we talk about the Big Bang after Thanksgiving, not the show, the TV show, but the event that unfolded the universe, I like that word unfolded, we're going to see that this idea of these weakly interactive massive particles are kind of help make sense of the Big Bang to the present time. Okay, so for instance, this slide actually, this might look familiar to you. This is a protogalactic cloud. Okay, kind of condensing almost to ultimately form a galaxy of stars. We talked about this in the chapter on galaxies. And it's the presence of these weakly interactive massive particles that actually kind of help this process. Okay, so one of the things we talked about earlier in this chapter is the fact that all galaxies have this dark matter around them. So you kind of see this sort of light-colored stuff, kind of ghost-looking stuff, that is dark matter around a galaxy. Okay, and so you see the disk and you see the halo region of the galaxy, then you see this dark matter. And so actually we kind of think that it needs to be there, like I said, in order for the galaxy to form stars. So this actually reminds me of, if you've ever played with those little things where you have a magnet and you can kind of make faces, you can make mustaches and things on something's face using metal filings. This is what this reminds me of. But if you look closely, each one of these is kind of a little arrow, and it's showing you the motion of a galaxy. And the motion of a galaxy of stars where they are coming together in these sort of filaments. So galaxies, we said, are organized into clusters. And, actually galaxies are kind of falling in towards this invisible thing that we think that there's a fair bit of this dark matter there. Okay, so speaking of galaxies and the organizations of galaxies, these little yellow dots actually are not clusters. These little yellow dots are galaxies. And you can kind of see the three sectors from left to right. And these three sectors were taken with, as I understand it, are the location of galaxies using different techniques. Okay? So we are right at the leftmost point from our perspective. We are just a star. We are orbiting a star, one of 100 million stars, 200 million stars in our Milky Way galaxy. Maybe 200 billion stars. I'm going to check that. And actually, you kind of see some blue area. The blue area is where there's nothing. There's no galaxies, no nothing. They call those voids. So that first sector actually is the closest to our galaxy. And there's what they call a great wall of galaxies, and that's kind of like this filament, sort of I was saying a minute ago, where this kind of stringy nature right here, kind of stringy nature right there, kind of a wall of galaxies, and that would be where kind of dark matter is kind of hanging out. Going on to the next sector, okay, this wedge was taken from a different survey, and it also has kind of a filament or a wall of galaxies. Okay, so again, kind of these walls of galaxies make sense as to there are these weakly interactive massive particles that have been here ever since the Big Bang, and they kind of help the organization of our universe. So galaxies are organized into clusters, and clusters of galaxies are organized into superclusters of galaxies. Is that not silly or what? And the space between these superclusters are called voids. And I don't know if you can see it very well, but up there at the top, it says, you might be wondering why in that third sector it looks kind of sparse. And it's not that necessarily there are not a bunch of galaxies out there. It's just that, like the caption says, they're kind of dimmer, so they're harder to see. So, like I said, after Thanksgiving, we'll talk about the Big Bang. But this is actually, 500 million years after the Big Bang, 0.5 billion years after the Big Bang. When the universe was smaller, and like we know, I'll go ahead and kind of advance to now. One of the things we know is that our universe, the fabric of our universe, literally the thing that you step on in our universe, has been expanding. Okay, it's been expanding ever since the singularity unfolded, about 13 billion years ago. Yeah.
If it's expanding, what exactly is it expanding into?
What is it expanding into? I've watched, maybe like you have, many documentaries on that. It's expanding into, there's different thoughts on that, but I would say it's expanding into nothing. And my thought is that there are actually multiple universes. That's my thought right now. Okay, so that's a really good question. And the multiverses, actually multiple universes, then you figure multiple universes can interact, and actually that's where we can talk about universes expanding and contracting and interacting. There's something to be said for that. But this is our universe getting larger and larger, the fabric of space and time. And this is actually on the test you just took, why galaxies interacted a lot more early on than they do today. Okay, so if I play this, which I'm just curious if it will play, it should play. This is then kind of showing you the stringiness of each kind of clump is a galaxy. It's not a star. It's an island of stars, a galaxy of stars. And you can kind of see the fragmentation kind of creating stars within those galaxies. Okay, it's something kind of like we've been looking at. How do you make stars? Well, you have to have some sort of contraction, and these are galaxies of stars. And you can kind of see the filaments in the void areas. Very pretty. Okay, so now I'm not saying I could, say I entirely understand it. But like I said, if you're an astrophysicist, this idea of weakly interactive massive particles, at the time, ever since the Big Bang, kind of makes sense for actually needing to be there in order for protogalactic clouds to form galaxies of stars. All right, so the last topic, and we're not going to go on to the next chapter, but this last topic is kind of, again, the expansion of our universe. And it's kind of like what Hannah was saying. What are we expanding into? And again, we'll talk about that thing. We'll talk about the Big Bang event, and kind of what was associated with Big Bang event is this little point called singularity. And we actually have talked about singularities before when we talked about black holes, okay? But here we go. So this is going to kind of remind us that gravity is a player. If you're the universe and you want to expand forever, all right, okay, well, you might have something playing against you, and that would be gravity, okay? So not necessarily an expansion of the universe, but if you are simply a cannonball and you want to escape the influence of gravity of the Earth, okay, well, good luck, right? So every object, I guess every object, has this thing called escape velocity, okay? So in this case, going 10.9, so it looks like units or kilometers per second, that cannon did not have the right speed, enough velocity to escape the gravitational influence of the Earth. Now, the other thing about speed, or a moving object like that cannonball, all moving objects, and I think we talked about that in this class, all moving objects have a certain amount of energy called kinetic energy. And the kinetic energy that an object has, actually, KE, is it going to let me write on this? No, I guess not. Kinetic energy is equal to 1/2 times the mass of the cannonball times how fast it's going squared, 1/2 mv squared. So the point here is and actually we saw Neil deGrasse Tyson do this, if I go ahead and bump up the speed at which the cannonball is flying, okay, it will eventually, like he said, I think he said your grandparents say an apple that you throw up in the air will never leave the earth, and that's not true. If you throw it, it will leave the surface of the earth. So let's go ahead and bump this up from 10.9 to, okay, let's see, what do I got now? Still got 10.9. Okay, let's go 11, and I'm going to fire. Oh, so close. Okay, so it didn't have, it did not reach the required escape velocity, but thought another way, it did not have enough kinetic energy to escape the gravity of the Earth. So let's go ahead, and whether it's an apple or whether it's a cannonball, let's jack it up, because I can never remember. Let's go ahead and jack it up to 11.6 kilometers per second. Fire! Whoa, finally, we were going fast enough. We had enough kinetic energy to basically escape the gravitational influence of the Earth. Okay? So how that relates to the expanding universe is this. Actually, there are, and I'm sure there are more, but I'm going to show you 3 and then a 4th scenario of the Big Bang. So, and again, I'm kind of, these chapters kind of go together. This is 18. We'll talk about 17 after Thanksgiving. But that little star thing right there, that actually is the universe unfolding. And the little orange line there is the present day. And so anything north of the orange line would be, what is our universe going to do? So one scenario is this. And if you've ever heard of the Big Crunch, okay, this is what they're talking about. Basically, it says our universe expanded and it's going to recollapse again. And why would that be? That would be actually if we have a lot of matter, if we have a lot of mass. It's basically going to come back on itself. Okay. Another scenario is if we have just the right amount of mass. So the difference here is not a big crunch, actually, and it's not the big freeze, okay, but it's more, it will basically, kind of like we saw that cannonball leave the surface of the Earth a little bit ago, it will just kind of coast, because it did not look like that cannonball was really going to kind of keep speeding up. It's just kind of coast, okay. That means we have just the right amount of matter. And most of the matter of the universe is dark matter. So, at the time of the Big Bang, we had the right amount of dark matter. Okay. So here's another scenario, though. So here we have the Big Bang. And notice the difference between, if you call them A, B, and C from left to right. The difference between B and C is that actually C shows us that we are going to continue to expand. And C actually, if you do the math, the way we know that energy works, is that C is the situation in which basically you have less than the critical amount of matter as compared to the energy of the original Big Bang. Okay? So that's the deal. And if you look at the side there, the words say that we know how much matter there is in the current universe, and actually the matter in the current universe is associated with the matter that was at the time of the Big Bang, and we're about 25% of critical. So we actually we are more C than A or B. But it's interesting how if you look back 20 years even, I bet the Big Crunch was still in being talked about. Okay. This is the 4th scenario, so this would be D. And actually, this is what Hubble saw when he compared how fast galaxies are moving away from us, the farther away they are from us. He said actually the farther away galaxies are from us, the faster they're moving from us. And that's not just from us. You could extrapolate to basically all galaxies that are far away are moving faster, okay, so this actually means, the reason they're moving faster, by the way, is because the fabric of space and time they hang out in is expanding, okay? So honestly, it's not just that we're coasting, okay, we are accelerating. And if you remember one of the things that Newton said, force is equal to mass times acceleration, Basically, you don't get something for nothing. You don't get an acceleration without a force. And what I'm going to say in a minute is that force actually is the other dark thing. That force is dark energy. Okay. So putting them side by side, here you go. Here are A, B, C, and D. And like I said, D is the real deal. D matches up with Hubble's law. Okay, D matches up with the amount of mass that is in the universe, and it's definitely less than critical. So here's the deal, and I also want to kind of point this out. I said that Hubble's law, we can actually use the slope of Hubble's law, Hubble's constant, to get an age of the universe. And on your test, this test you just took, you said it was 13 to 15 billion years old. Okay, the age of the universe. And I said there were other ways that you could calculate the age of the universe. And another way is this. For each one of these scenarios, whether our universe is going to have a big crunch, whether it's just going to kind of stay the same size, whether it's going to continue to expand at a uniform rate, or whether it's going to continue to expand at an accelerated rate, for each one of those scenarios, actually you can go back in time and see when the Big Bang was. Okay, it's math. It's funny. People cringe. I don't know why we cringe when people say, well, how do I do that? Well, you need to have math. Okay, but my point is that actually this last scenario with an accelerating universe, accelerating due to the presence of dark energy, actually gives us the longest time ago of the Big Bang. Okay, another way to gauge how old our universe is. So I forgot I have just a few more slides. Okay, so I'll go ahead and kind of put these up here. Top to bottom, the top is with no supernova, and the bottom one is a distant galaxy in which a supernova has occurred. I just think that is so cool. Okay, and we talked about this idea of redshift, and the more the redshift, let me go ahead and pull up my pencil here. Okay, the greater the redshift, okay, the faster it's moving from us. But not only that, what the cool thing about this is we can use these as, like the slide says, as standard candles. Oops, I butchered that spelling, but you get the idea. Standard candles to get distance. So these galaxies, which have these standard candles in them, we can get distance and we know how fast they're going. So we understand how in that neck of the woods the fabric of space and time is expanding. So we have seen a lot of scatter plots this semester. This is another scatter plot. Now all of those symbols up there actually represent galaxies in which supernova type 1a has occurred. And in those galaxies, of course, we can use redshift to get to recessional velocity, and we can use standard candle to get to distance. So what you're looking at here are the four scenarios, the A, B, C, and D that we talked about before. So the crunch was here, okay, the critical was here, the coasting was here, and actually evidence suggests that we have an accelerating, the expansion of our universe is accelerating. So again, doing the math, you can kind of see with regard to behavior of these current. So this is raw data right here. Well, I don't know how raw it is, but it's data, okay? That actually, the point is that we are more on the D line than we are on any of the other three. Okay. All right, very good. Okay, last slide, which some of you have no idea because no one printed it out. Okay, have a great weekend.